Hey everybody, in this video we're going to start by looking at a number pattern. We're going to start by putting out two ones out here, and we're going to kind of create a little pyramid, and on the outside of the pyramid we're always going to have ones. And then on the inside of the pyramid what we're going to do is we're going to add the two numbers that are flanking it or kind of above it in the pyramid. So 1 plus 1 is going to be 2. So following this pattern we're going to put ones on the outside, and now we're going to add 1 and 2 and we'll get 3, and we're going to add 2 and 1 and we're going to get 3. So now we've got this line being 1 3 3 1. Continuing on, we can have 1, we'll add together 1 and 3, we'll get 4, 3 and 3 is 6, 3 and 1 is 4, and then 1 on the outside. We'll do one more row. So we got 1 on the outside, 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5, and 1 on the outside. So if we continue this on, this is a famous triangle called Pascal's triangle. Now there are instances of this found in nature, and what we're going to do though is we're going to look at it, how it applies in some algebraic instances. So let's start by looking at a plus b to the first power. Now if we were to expand this out, there's actually nothing really to expand, it's just going to be a plus b. But what if we took this a plus b and we put it to the second power? Well, now we're going to use, or we're going to have a plus b times a plus b, and we're going to use FOIL or distribution or whatever methods you like to use, and we will expand this out a little bit further. We get a times a, we know that's a squared. We got a times b, so that's going to be ab. Then we got b times a, that's another ab. So we have two ab's, and then of course b times b, which is b squared. Taking this one more step, if we to go a plus b cubed, and that's going to equal, well, a plus b times what we just multiplied above, a squared plus 2ab plus b squared. You could say a plus b times a plus b times a plus b, but why go through that work if we've already done it in the step above? Okay, so now we're going to distribute our a. We're going to start by a and a squared, so that's going to give us a cubed plus a times 2ab, so that's 2a squared b, a times b squared, so we got ab squared. Now we have to do the b, so we multiply b times a squared, and we get a squared b. And continuing this on, we see our nice patterns, 2ab squared and lastly b cubed. Alright, so let's simplify, get some like terms together. We got a cubed, there's no other cubed terms of a. But we do have 2a squared b, 2a squared b terms, but when we add them together, that gives us 3a squared b. We also have two terms in this distribution, or this expansion I should say, of ab squared. Add those together, we get 3ab squared. And finally we have our b cubed. Now you're probably recognizing this already, that our coefficients of ab are 1 and 1, and that matches the first row of Pascal's triangle. The coefficients, the number in front of the variables, for the second one is 1, 2, 1, and that lines up with our second row of Pascal's triangle. And obviously the third 1, 3, 3, 1 matches up with the third row of Pascal's triangle as well. This is called a binomial expansion. Binomial because we're multiplying binomials together to different powers, but it's binomial expansion because expanding we're multiplying it out, right? Alright, so what are we going to do with this? We're going to look at the exponents, and we're going to look at a lot of different patterns. So if we look at the exponents, we've got a to the first power, a to the b to the first power. And it's interesting to note as well that as we go throughout, we have a squared, a to the first, and then we also have b to the first, b squared. And down on the third one, we've got a cubed, a squared, a to the first, and a to the 0 power. We didn't write that anywhere, but anything to the 0 power is 1, so we could still include that just to help keep track of the pattern. Similarly, with the b, that's going to be like b to the 0 power, So we're starting down and we're going to count up because b to the 0 power is 1. We don't really count it, but again, you can put it if you'd like. And then we've got b to the first power, b to the second power, b to the third power. So in this binomial expansion, what we can see is that the coefficients are the applicable row of Pascal's triangle, and the variables, if there are variables in your binomial, the first variable is going to decrease. We're starting by the same power that we're multiplying out, but it's decreasing by 1 in every exponent. And the second variable, the b variable, is increasing by 1 as we go across. So just some interesting patterns. And we can take this and we can look at these things as combinations. We can look at our Pascal's triangle as combinations as well. Combinations are commonly written as NCR, and NCR is when n is the number of items in a group. So we're looking at the number of items that we have in any grouping. And our R is going to be the number of, or how many we're going to take at once. So how many taken at one time. So let's look at this in an example, but before we get to the example, okay, one last notation bit here, and then I want to look at an example of how NCR works. So we can also call it n over r. Well, it's not really over because it's not a fraction, but we've got n of r. So we've got the number of items and how many items we're taking at one time. So both of these things are the same way to write combinations. Now, we're using combinations because combinations fall in line with one of these patterns like we're looking at above. So let's say we had 5 letters, A, B, C, D, E. And we're going to look at how many times can we take no letters at once. So here, 5 of 0, I'm sorry, that's 5 items, A, B, C, D, E, and we're taking none of those items. Well, there's only one way we can do that, and that's by not taking any of them. What about if we wanted to take one item from here? Well, okay, so now we're looking at our 5 items, and we want to take one at a time. How many different ways can we take one at a time? Well, we could take the A, we could take the B, the C, the D, the E, and there are 5 different ways because we could take each one once, right? So there's 5 different ways that we could do that. What if we wanted to take, if you notice, this does follow Pascal's triangle, right? So this is starting to follow. So what we should get is if we have 5 and we're taking 2 items at a time, we should hopefully get 10 if we're following the same pattern. So we could let's list it out. Maybe that will be the best way to do this. So we could have AB, AC, AD, and AE. So that's all the different ways that we could take A and another letter. Now let's look at all the different ways we could take B with another letter. So we got BC, BD, BE. Now we don't count AB again because whether you're taking AB or BA, you still have the same combination. So we don't repeat anything. Okay, so then with our C, we're taking CD and CE, and then with our D, we've got DE. All right, so how many is this? We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 of these things, and we can see that this pattern is going to follow the same as Pascal's triangle. Now, in another video, we'll go through some examples of how you can apply this, but it's interesting to note how these things tie together, how we've got Pascal's triangle, how it falls in line with these the coefficients of this algebraic binomial expansion, how it also falls into the same expansion of combinations, and then within there we have these patterns of increasing and decreasing exponents of our variables. So it'll be interesting to see how we can apply this, but we'll do that in another video.